Hello everybody, welcome back to Glaciers and Glacial Geomorphology. In this session we're talking about glacier temperatures and the basal thermal regime. In the last few sessions we've been talking about topics that have led us to think repeatedly about temperature. Temperature in the glacier has impacts on all sorts of different components of the glacier system, and as we work our way through our big conceptual map of how glaciology hangs together, from the big global system, the hydrological cycle, through glacier dynamics, how glaciers move, and heading on now towards glacier geomorphology, how glaciers affect the landscapes around us, a few key topics keep cropping up. One of them is temperature. We've seen temperature affecting in Glenn's flow law. We've seen temperature affecting water at the base of the glacier, permitting or restricting the amount of sliding that's going to be carrying on at the base of the glacier. Temperature has occurred when we've talked about basal ice, the entrainment of debris into the basal ice layer. When we were talking about supercooling, the impacts of supercooling both on basal ice formation and also, as we'll see later on geomorphology. Well, obviously supercooling, well, that's all to do with the basal thermal regime, the interactions between temperature and pressure and processes going on at the bed of the glacier. So glacier temperature is a really important topic for us to say something about. The first thing that I want to say something about is simply, well, what determines the temperature in a glacier? What are we talking about? Surely glaciers, well, they're cold, they're frozen. Isn't that the end of it? Well, no, that's not the end of it, because glacier ice can occur at a variety of different temperatures. Different glaciers are at different temperatures, different parts of the same glacier are at different temperatures, and the temperature within a glacier, even at any one location, particularly for example a location at the glacier bed, can change through time depending on other things that are going on. And certainly as we move through a glacier system, for example as water transits through a glacier along the bed and out at the margin, it's going to be experiencing very different thermal regimes, very different temperature conditions at different points in that journey. So we have melting, we have freezing, we have all sorts of different things going on. So even in a very simple case, if we have a glacier surface, the glacier and the glacier bed, we can identify a number of very straightforward parameters that are determining what's happening with glacier temperatures. Are we going to be close to the melting point, close to zero at atmospheric pressure, or are we going to be in colder ice down to -10, -20, -30, -40 centigrade, compared with ice close to zero, close to that melting point. And we talk about warm ice, meaning ice which is close to the melting point, and cold ice, which is well below the melting point. And you're already familiar with issues such as, for example, the fact that warm ice is softer or more ductile or more deformable than cold ice, which is harder, more rigid, less deformable. So what determines the temperature at different points in a glacier? Well, the first set of conditions relate to things that are going on at the surface. For example, the temperature of precipitation which is accumulating on the glacier surface, and the temperature at that surface location. And that's going to contribute towards essentially the burial of a particular temperature profile or a set of temperature characteristics into the surface of the glacier. That's also going to be modified by melting and refreezing in that surface zone. So snow melts to produce water. If that water percolates into the snowpack and then refreezes to produce ice, well, then we're dealing with the release of latent heat, or the absorption of latent heat from the environment, and that's having an impact on the temperature. So there are a number of things going on in that upper layer that are leading to the burial of ice of a certain temperature into the glacier. Now you might be thinking, yeah, but this varies through the year. There's summer and there's winter, temperatures vary. You're absolutely right. So there's a winter temperature profile and there's a summer temperature profile, and then this upper portion of the glacier, well, temperatures are going to vary through the year. So we have a zone very close to the surface of the glacier. People sometimes talk about it being about 10 metres, but it varies a lot from glacier to glacier. But in the upper few metres, say the upper 10 metres of the glacier, the temperature varies through the year, warmer in the summer, colder in the winter. But as we get down to that 10-metre depth and below, the temperature profile settles out, and people sometimes talk about the 10-metre temperature as being roughly equivalent to the mean annual surface temperature at that point on the glacier. There are complications to that. For example, this stuff to do with the latent heat processes, but roughly speaking we can talk about the 10 metre temperature as being roughly equivalent to the surface temperature of the glacier there, and that is then being buried down into the profile of the glacier. You then might be thinking, yeah, but not only does temperature vary through the seasons, it also varies over long time periods. Climate change. 200-300 years ago, the Little Ice Age, surface temperatures in lots of glaciers, lots of parts of the world would have been colder than they are today. You're absolutely right. And so we get the burial of essentially what's called a paleothermometer. Ancient temperatures from the glacier surface can be preserved lower down in the glacier as more accumulation occurs above it, and we're burying ice at a certain temperature into the glacier surface. So at a particular glacier now, maybe the surface temperature is about, say, minus 10 degrees centigrade, but maybe back in the Little Ice Age it was a few degrees cooler than that. Well, if we were to drill down into the glacier, you would anticipate that perhaps temperature decreases with depth. If we draw a temperature against depth profile here, maybe you think, well, you've got the variable bit in the upper portion of the glacier, the top 10 metres, but then maybe it gets cooler with depth because we're going back into ice from colder periods in history. But then what happens as we move through this interior zone? We've talked about the surface processes burying a surface temperature profile into the glacier. Well, in this interior zone, as you know, we have deformation, we have strain processes going on. So you'd anticipate maybe a little bit of warming from strain heating in there. Also remember though, of course, we have horizontal advection. Ice from further up glacier is being carried down glacier and through the point where we're drilling our profile. So perhaps that's bringing colder ice in. So complicated things going on in this end glacial zone with both local warming but also potentially cooling by advection of ice from upstream. But what's happening at the base of the glacier? And here we have heat from the interior of the Earth. We have geothermal heat flux, a significant amount of heat being provided to the base of the glacier there. We also have movement at the bed, enhanced strain close to the bed, but also sliding across the bed generating friction. And so whereas you can, in a very general kind of way, think of cold being buried into the surface of the glacier, you can think of warmth being introduced from the base of the glacier. And the rate at which this cold is introduced, which is partly going to depend on the accumulation rate, are you putting more and more of that cold snow in at the top very quickly, or do you have a very low accumulation rate and you're only bringing that down into the glacier quite slowly? Well, how's that going to fight against this provision of heat from the bed of the glacier? And in general, this provision of heat from at the base of the glacier is going to lead to an increase in temperature with depth as we approach the bottom of the glacier. So we generate this general mixed, potentially cooling depending on climate history, but then warming because of end glacial and basal processes, a warming profile as we head towards the bottom of the glacier. And I'll show you a little bit of that in more detail in the next set of slides. So these slides will just guide you as you start to do some reading and put some detail onto these general issues about glacier temperature, and then we'll move on and talk more specifically about the basal thermal regime. But first of all, let's just carry on talking about glacier temperature more generally. And there are a number of specific points that I want you to think about, and as you're doing the basic reading, have these points in your mind as well. First of all, what is the temperature profile? What are the temperature characteristics of glaciers? How do temperatures vary within glaciers? That's the first point. Secondly, well, why is that? What are the controlling factors? What determines those temperature characteristics? And thirdly, as always, it's the who cares question. Who cares? Why? How is the thermal regime, how is temperature important? Both in glaciology, kind of looking back through the course, thinking about glacier dynamics and those issues we've talked about previously, but also thinking forwards through the course, looking forward to glacial geomorphology and how the temperature in a glacier system can affect glacial geomorphic processes and therefore affect landforms. So those are the topics that I want you to be thinking about as we're talking about this topic of temperature in glaciers. Well, you already know lots of the reasons why temperature is important in glaciers because we've talked about them in different contexts earlier in this module. For example, temperature controls ice rheology. i.e. the flow properties of the ice, the way that ice moves. For example, Glen's flow law, E equals A times tau to the n. A is the hardness parameter. It's commonly referred to simply as the temperature dependent hardness parameter, because temperature of the ice is such a key control on the deformability, the hardness or softness of the ice. There are other controls as well, such as particulate and dissolved impurities, but temperature is a key component, a key control on ice rheology as regards to deformation, creep of ice. Now that therefore determines, or that impacts upon glacier dynamics more generally. So I've put there on the slide both internal deformation, so Glen's flow law for example, subglacial deformation. The deformation of a substrate underneath the glacier is to a large extent temperature dependent. If the substrate is frozen, if the substrate is not frozen, if there's high basal water pressure or not. Temperature has a major control on internal and subglacial deformation and on basal sliding, the sliding of the glacier across the bed. You remember the Whammo surf rider slip and slide example that we used when we were talking about glacier sliding. If you don't have water at the bed, sliding is harder because of the lack of lubrication, and if the temperature is low, so any water at the bed is frozen, so if the glacier is frozen to its bed, cold-based glacier, sliding is again much harder to accomplish, and so you get much less sliding. And already now you can begin to think of the implications there for glacial geomorphology. If you're not getting much sliding, you're not getting much movement at that interface between the ice and the bed, what are the implications of that for geomorphology? Also relevant to geomorphology is the general issue of glacier hydrology and water production. That's really important both to glacier dynamics and to glacial geomorphology. And water is a major part of the glacier system. We haven't said a great deal about it yet, but we've encountered it on a few occasions, and it's something that we might talk about in a lot more detail later on. But in most glaciers, water is a major part of the glacier system, not just because of its geomorphic impact, but also because of its impact on the way that the glacier moves, and also as an indicator of what's going on in a glacier. By studying water, we can learn a lot about the glacier as a whole, both in terms of the chemical composition of the water, the debris content or sediment load in the water, and the very presence or absence and the timing of the release of water, for example, from a glacier. Water is really important, and water is temperature dependent in glacier systems. We talked recently about the basal ice layer and the entrainment of debris into the basal ice layer and the importance of the basal ice layer to a glacier. Well, all those processes that we were talking about when we were considering basal ice, for example, the refreezing of meltwater at the bed to stick new ice with debris onto the base, even the flow of water through the vein network, which was one of our hypotheses for the origin of the dispersed facies or the clotted ice facies, all of those processes that we were talking about in the context of basal ice are temperature dependent. So the temperature at the bed of the glacier, what we'll talk about in more detail in the second part of this unit, the basal thermal regime, that's really important for basal ice, and basal ice is really important for lots of other things in geomorphology, including, the last thing on the list there, geomorphic processes: entrainment, transport, deposition of sediment, erosion of the substrate. All of these things are dependent either directly or indirectly on temperature and the basal thermal regime, either because they're dependent on water, or because they're dependent on the movement of the ice, or because they're dependent on processes associated with the entrainment and transport of debris and the formation and behaviour of the basal ice layer. Everything is tied together. You remember this from what we've talked about previously. You're making your map of how everything connects, and this slide, I guess, is a nice illustration of that. That you could, in fact, that would be a nice it would be a nice exam question if we had an exam paper for this module, would be to give you that slide and say, draw me the arrows, draw me the connections, turn that into some kind of a flow diagram. I'm talking to the first years about systems at the minute. Try drawing some kind of a systems diagram to illustrate the connections between those components where temperature is playing a key role in the glacier system. So there are lots of, short answer, there are lots of reasons why temperature is important when we're studying glaciers. And I've drawn this little, I don't know what you'd call that, little illustration there, just to help you maybe get your head around the most basic ideas of how you might start fitting this little component into your big map. Just what from some of the things we've talked about already. Temperature is related to movement, it's related to hydrology, movement and hydrology are related to each other, and movement and hydrology, I put it to you there. Again, think of this as an exam question with the word discuss at the end. I'm offering to you there the idea that geomorphology is to a large extent, well, according to that diagram, completely, but take that with a pinch of salt and think about what else you'd add to this diagram. But geomorphology is controlled by movement and by hydrology, and movement and hydrology, as well as interacting with each other, they interact primarily with temperature. Think about that. There are obviously lots of other arrows and lots of other boxes that we could add to that diagram, and eventually it will turn into your big map of the module. But for now, I just want to use it to emphasize the importance of temperature and the connection of temperature with some of these other big topics that we're talking about. So in the earlier part of this video at the whiteboard, I mentioned a number of different factors controlling temperature. So just to put those in writing for you here, in case you're trying to organise some notes around what we're talking about, you can always pause the video, stop listening to me, and just have a look at what's on these next few slides. Don't remember, you can always do that. You can pause me to shut me up, you can rewind me, you can fast forward me if you want. But be aware, first of all, of a variety of surface controls, and having a look at the textbook alongside these video lectures, make sure that you understand how each of those surface controls that I've listed there are particularly are relevant as controls on temperature. So we talked about what's happening at the surface of the glacier, and there are those factors there to take into account. I don't trust you to pause me, so I'm pausing briefly to let you look at those. The second of this set of slides here, internal and basal controls. As well as having essentially coldness being poured into the top of the glacier, we also have things happening in the interior of the glacier, and we have things happening at the bed of the glacier. So again, I've just listed a few of those there. I mentioned those on the whiteboard earlier, but just pause me, have a read through those. Go to the textbook and look them up if you're not sure what I'm talking about, if you don't understand what the differences are, or how we're getting latent heat transfer or melting freezing. If that's a bit of a mystery to you, just go and have another little look in the textbook, or stick it on the discussion board on the KLE, and I'll pick it up in the lecture, in the live lecture at the end of the week. So the surface controls, there's internal or basal controls, and as I said, there's this typical pattern that emerges from those controls, where, as you can see here at the top of the glacier, there's that supposedly 10 metre or so layer where the temperature varies through the year. So I've put the temperature curve going both directions, off to the left for colder in the winter and off to the right for warmer in the summer. Then with depth, ignoring the possibility of past climate change burying colder temperatures into the upper layer of the glacier and therefore giving us that cold wave. I've ignored that in this diagram. Ignoring that, you'd expect that with depth there'll be an increase in temperature. Now here's something for you to think about. Why have I drawn that temperature curve as a curve? Why isn't it a straight line going down with depth? Why have I got the rate of increase of temperature with depth increasing with depth? Why does that curve off to the right rather than just being a straight line? Again, that'd be a nice little question in your end of module workbook, for example. That's the kind of question that I might ask you, just to explain what's going on with that kind of relationship. And if you look in the literature, this is from Robin's old 1983 book, but you can find lots of these in the literature. You can find examples of profiles through ice cores drilled through glaciers where they've measured the temperature at different depths in glaciers, and you'll see that in general there's that general trend towards warming with depth, with the warmest temperatures being closest to the bed. But you can also pick out in some of those, some of them are like the diagram I drew, some of them are more straight lines. So what's going on there? Why is it variable? And some of them do indeed have this initial, as you go down from the surface into the upper portions of the glacier, they have this initial curve to the left, to the colder conditions. So what's going on there? And here's a slide that I've just taken from Blatter's work at the White Glacier on Axel Heiberg Island. And this slide, which again you might want to just pause and have a little look at in more detail, but basically it's showing isotherms, temperatures through the thickness of a cross section through the glacier with boreholes drilled into it to measure temperatures. And what it's showing there is that the temperature is initially cooling with depth. So there's a cold heart, if you like, a bit like myself, there's a cold heart in the middle of the glacier, a cold layer. So initially with depth we're getting cooling before then getting warming. So in that bottom diagram there, we're at minus 10 or something at the surface, but then it goes colder, minus 11, minus 12, minus 13, and then it starts to warm up again, minus 11, 10, 9, 8, 6, and warms up closer to the bed. So that's an example of this buried cold layer, the paleothermometer effect, the ancient temperatures from the surface being preserved as layers of cold, historic ice are being buried into the glacier before those cold layers eventually do get warmed up by processes in the interior and processes happening close to the bed. So be aware of these complications, and be aware of the importance, the value of these complications, for example, for reconstructing past climates or correlating past climatic changes with layers in the glacier. Could you use it as a way of dating the glacier? For example, if you have a historic record of temperatures at the glacier surface and you have the ice core record of temperatures in the glacier, is that some way of dating the glacier ice, the layers in the glacier? Lots of things for you to think about there. And here's a diagram that you've seen before, which kind of ties together. I got this the Earth Observatory site, but I put the reference to the original paper on the KLE if you're interested. But it just illustrates and draws together some of those in a general way, some of those points that I've made about the typical profile of temperature with depth through an ice sheet. And you can see on there all of the things that I've been kind of talking about. Modern surface temperatures, a bend to the left for the Little Ice Age, colder temperatures, and a bend to the right for the warmer temperature of the interglacial. Then here we're going so far back in history, we're then picking up the cold ice from the last ice age, 1500 meters depth there, before then going off to the right as we head towards the bed, and we're getting the interior and basal warming effects. Now I'm going to move on next to talk about the importance of temperature in basal processes, but I'm going to pause there and bring this particular video to a stop, because for this video I just wanted to introduce you to the idea of thermal regime and temperature in glaciers and how important it was and what some of the key controls are. And as you can see here, I'm going to come on next time, carrying on this unit, to talk about in the next video the importance of temperature at the glacier bed, and that will give you some indication of a particular application of our knowledge of glacier temperatures to some of the specific questions that we're really interested in about glacier dynamics and the impact of glaciers on geomorphology and the formation of landscapes. Save that for next time.